Is it busy? नहीं ये पूरा खुला है मैंने ओपन किया ओके सर Okay, should we start? Okay, I hope it's not getting too much. We have got a short break as well. So let's restart. So in the morning, I have shown you this slide and the plan which we were trying to implement for today. So first two tasks we have achieved. Now we are left with three more things to do. Okay, so firstly will be, I'll just briefly go through the things that we have learned yesterday, and then we'll do some addition. Then it would be because we have already understood the algorithm. I'll just briefly give the overview so that you can implement it, and with the basic some terminology which we very frequently use for such kind of problems. Okay, then we'll try to solve it for a simple given some data from cosmology. Some of you must be familiar with it. It might be new for some of you, but consider it to be just a simple data set, nothing more than that. Okay, and then we'll briefly talk about the package. I'm going along with the examples or the collab files that I'm showing you. I'm going to share all of these with you. I'll share it immediately after the lecture today. Yesterday I shared it quite late. So you can do it today by tomorrow morning, and maybe when I'll be here tomorrow, then we can have a discussion about it in case you're stuck somewhere. If you are working on some project yourself, and because I'm going to show you a very simple example with Hubble data. Let's say some of you are working, I know some of you are from cosmology as well, and you are yourself kind of stuck somewhere. You are using a completely different data where a lot of error or different matrices, correlation matrices are there. We can have a discussion about that, but that will be depending on the personal interaction when you'll meet me. Okay, I'll not be discussing it here because we have this time constraint as well. So let's go to our third thing, which we were doing yesterday. If you remember, I was talking about, I have shown you this distribution yesterday. Just give me 1 second. It's a bit slow. There is a bit of lag between. We have discussed it. Yes? Yes, ma'am. We have seen this distribution. So in this particular Metropolis algorithm, we come across 2-3 terms. One was the initial point, initial value that you were giving, or you can call it the initial seed. So by using the initial seed, you were starting from a point, and after that, because your algorithm was based on the something called Markov-Chain Monte Carlo. So in Markov-Chain Monte Carlo, had it been a Monte Carlo method, the next random point that we would be throwing, we will throw it randomly. Okay, we'll not worry about the previous position. But the moment I am going to worry about, or I'm going to take care of my position before throwing the next point, I'm going to consider the previous position in. I'll take it in consideration. The moment I'll do that, my way of throwing random numbers or creating the sample will become Markov chain based. Okay, so now how we are going to throw the next point or next random number? For that, we were considering the distribution to be Gaussian yesterday, if you remember. That function you were choosing, that we were calling that the proposal function. So two terms, initial seed, proposal function, these two terms we have come across. Okay, now third thing that we will come across is about something called burnout phase. But what do we understand by the word burnout phase or burnout steps? If you remember this problem, I am just referring to yesterday's lecture. We were starting from -5, very far from the global mean. Yes. So if you'll use that global mean, and then you will see slowly, because step by step, your algorithm will be approaching to this local minima. and then we'll be approaching to the local maxima and the global maxima step by step. So sometimes when you will be doing the statistical analysis, when you will be creating a large number of data set, you will realize that your data will converge somewhere in the peak, around the peak. Converge means it will keep oscillating in the neighborhood of that particular given peak. But when you will do the statistical analysis, the initial part, which is giving you very, very far, which is just due to because you had made a random choice about your data or input point, this will be causing certain amount of statistical error. So to avoid that, what we do, we get rid of some of initial points. Let's say initial 1000 point or 2000 point. We will not take those initial points in our consideration when we will be doing the statistical analysis, because that was the path when we were leading towards the maxima. Once we are maxima, we created the random points, we find out their mean, we use that. But initial points we will, because that's a phase in which we are approaching to the maxima, that particular data points we can get rid of. And that's why we are calling it burnout phase, burnout steps, the amount of energy we are burning to reaching up to the maxima. Okay, so that's what we can do. I'll just show it to you. Yesterday we were running this program. So if you see this chain, this is the chain. First data point which you choose it to be -5. Once -5, now step by step it is reaching towards the answer which is you are choosing, and after that it is oscillating around this point. Okay, so you can easily see that this is converging at a value. If you take the mean, then the mean will be somewhere around 0.18 or something over here, if you'll take the mean. But if you take the complete data in the consideration, this initial points over here, can you see this point? They are going to cause the statistical error because they are very, very far, and they are not the actual representation of the distribution that you are having. Because you have chosen your mean to be very far, it's taking some time over there. So in our algorithm, I have taken care, just try to see this thing. If I'll run it, let me run the all the libraries again. Okay, let's see. It's done. Then I'm going to plot my target function or the PDF that we have chosen. I hope let me show you the PDF again. The PDF is this one that we were considering, this probability distribution function. Now, data points that we were choosing was 2500. Let's make it roughly around 5000. It might take a bit time, but it would give a comparatively better result. I have 5000 is nothing. Always run your chance with very, very large number, like in 1 million or at least of that sort or order. Let me get rid of initial 500 points. I am saying initial 500 points. Those are the points which I am utilizing just to move from initial point to that particular region of my interest. So I am getting rid of these 500 points. So I'm calling that, and when I'll be creating a chain, I'll not store those initial 500 points in my data. I'll not use those initial 500 points for my analysis. And I'll just run the program for this one. Okay, so out of 5000, now you can see 4044 points I'm accepting. If I'll go to the acceptance rejection, you can figure out. I'll doubt that hardly 200 or 300 points you will be getting. But with Monte Carlo algorithm, just have a look. Now I'll plot my new chain, which is going to be without the burnout phase. See, now there is oscillations over here. I have to create a large number still, but still you see that burnout phase we have. Okay, still I should reduce more. You will see even 500 is not sufficient. Okay, let me, instead of 500, let me 1500 points I should remove. Okay, 1500 I have removed, and then I am running this. Now you can see this point, this is oscillating around in a region where your mean will be somewhere. So whenever you start doing any statistical analysis, you are supposed to get rid of these initial points. How would you know how many points? Again, problem to problem, it's going to vary. You will run the complete chain first, then see how many points you are reaching to converge to your value. And depending on that, you will decide on this particular choice. Okay. In case you are running some program, initial, in general, if you have sufficient computational power, 10% of the initial point we generally prefer to reduce. If you are running 1 million point, then it reduce 10%, depending on your computational power or how much time it's going to take for you. Okay, fine. So this is one thing. But yesterday, even some of you were, let me plot it as well. It might take some time, but let's see what will be the plot. But meanwhile, let me highlight one point to you. Yesterday, even some of you pointed out one thing, why we are running a single initial point. See, remember one thing, when I am plotting a single, I'm starting with a single initial seed, I am getting a single chain. Okay, let's say I am running a single chain, Markov chain, and creating 10 to the power 6 or 10 to the power 7 random points. I'm creating a very long chain. But if I'll run my and then calculate the mean, I'll get an answer. But moment later, let's say you run your program again. The moment you will run your program, because now the set of random numbers is going to be different, your answer will be a bit different. You run it third time, you will get a different answer. So if you are writing a research paper, how would you get convinced like which answer is going to be correct, which value to choose for my exercise? Now you can see, if I reduced 15,000 points, it is giving me this distribution only. It is getting rid of this particular point. So it is not considering it. I should change my burnout phase a little bit more. I should have made it 1,000, sorry. Okay. But that's what I'm trying to highlight, that you should remove certain points from the initial, maybe 5-10% of the choice that you are making. Fine. Okay. Yeah. So let me get back to the point. Wouldn't it be a better choice that instead of starting with an initial seed, if I'll start with a large number of initial seeds, if I am creating a single chain of 10 to the power 5, 10 to the power 6 elements or 6 random number, let me do the same computational power, but let me run now 10 chain, and each random number, each chain having 10 to the power 5 steps. Yes. What freedom it will give me? It will give me the freedom. One chain will start from this point over here. One chain will start from here. One chain will start from here. And in that way, you will be able to completely span the space. Some of you were saying yesterday, if you remember, if I am starting with -5, this is not going beyond this point. Yes. Now, let's say I am having a local minima over here. Local minima, very small minima over here, but my data is not going in this region. How would I scan that? That will not give me that overall picture. Now, then in that particular case, it's always beneficial that one chain you start from this side, one chain you start from this side. So when you will be having a distribution of initial seeds as well, then all those initial seeds will be taking care of different aspects or different features of your space distribution. So that's why now we are going to come across two more terms. One term, how many initial seeds you are going to use. The number of initial seed you are going to say, we call them generally in the MCMC, we call them walkers. How many walkers? Walkers means, you Game of Thrones, those of you have seen Night Walkers. Yeah. So walkers means the how many initial seeds we are working with. Now, number of walkers, number of steps. Every walker, how many steps every walker is supposed to take. Okay, so in these are the 4-5 terms which we'll be talking about. Now I am going to start with a set of walkers. Okay, so roughly, if I'll just show to all of you. Okay, those of you are working in cosmology, you might have seen these kind of plots. I'll show you these corner plots. So there is a library in the Python called corner library. Okay, so corner library allows you to plot the correlation function in a very special diagonal type of plots. When I'll run my program for 2D, then it would be better. Let me just leave it for a while. So what I'm doing now, I'm going to run the same program, but instead of choosing one single chain, what I'll do, I'll run with multiple walkers. And every walker will be running a particular number of steps. So now what I am doing, I am starting with 10 walkers. 10 walkers means 10 different steps. I'm running my program. Every time it will start for a single walker, it will keep running. I cannot run it right now because number of steps I am choosing is very large. It will take some time for me to run. Then we don't have that much time, but I'll just show you the result. Okay. Each walker will be running 2 lakh steps. Is it? 2 lakh. Okay. 2 lakh steps each walker will be taking. 10 walkers I am allowing to run. Same program, nothing special. All of you are supposed to play with this sigma, which I have told you. 0.1 I have chosen. What was this? This was the variance of your proposal function that you have taken. You make it very large, you make it very small, and then see how your algorithm is going to get impacted. Very simple program, hardly will take you 10 minutes to understand and 15-20 half an hour to write down on your own this one. So if I'll run this, and I'm also getting some burnout time. How much burnout time? I am reducing 500 steps from each end. If I am going to run it, I am getting something of this sort. What is this? Oh, sorry, it's not coming there. Let me. What are these? These are 10 overlap chain. Okay. Now you are not plotting one single chain, you are plotting 10 chains. You will take the mean of all these, and that will give you a better representation. That will give you a better representation of the whole space. Okay. So that's why whenever you start writing your algorithm, histogram, you can see the previous histogram that we have plotted, and this one, this is this blue one. This is the histogram of the random numbers that you have created. This is a better representation of the inherent distribution from which you are creating the PDF. Okay. If I have pointed out or highlighted it yesterday as well. When we are going to quote our result, we are not going to quote this result because on the top you are seeing 0.183 plus 0.681. That's not the correct result because I'm calculating this mean and variance by assuming this distribution to be Gaussian. It's not Gaussian. Okay, so that's why in MCMC, whenever we quote our results, we don't quote the mean and variance. Instead, we quote the median and the percentile. Okay, so that's why the correct way of doing it, I'm doing it by using this library. These are the quantiles. Those of you can, I'll just tell you about this quantiles library. Can you see these numbers? 0.16, 0.5, and 0.86. Let me show it to you. How is it working? It's important. Otherwise, whenever you are going to have a distribution, something like this. Okay. I'm going to choose minus infinity. Let's say this is going from minus infinity to plus infinity. Okay. When we define the percentile in the quantile, this point at the, let's say I'm choosing some very far point, minus infinity. Over here, I am going to say it 0. Okay. And at plus infinity, I'm going to call it 1. Percentile means obviously the total data is going to be between 0 to 1. On the leftmost, I am 0. On the rightmost, I'm going to be 1. From this 0, I want to find out the median. Where will be the median? Because median is going to be in between wherever it's going to be. So this is going to be 0.50 if this is a median. I'm assuming it. Obviously, half of the point you are dividing. Now, if you want to make the percentile to be 34%, so obviously you have to go 34% is this side and 34% this side. It need not to be uniform on the both side as well. So when you are going to 34% this side, so this point will become 0.16. And when you will be going 34% this side, this point will become 0.84. So what you are doing in your program over there, when you are finding out percentile, you are saying what is the value at 0.16, what is the value of 0.5, what is the value of 0.84. You calculate these three values, and then this error, it's going to give you negative error. This will be your median value, and this one will give you the positive value. Okay, that's what we are doing. Let's go to the program and see this. Yeah, that's right. We are defining the quantile. So 0.16, 0.5 value corresponding to 0.5 is telling you about the median value. This is important. And please, whenever you work on these problems, quote your results very cautiously, like in the sense what exactly is the meaning of these results. Okay, so now if you do this exercise, the representation for this data is 0.28 plus minus 0.47 minus 0.88. Ideally, how are we going to read this result? This 0.28 is not the mean, it's the median. Plus 0.47 is not the one sigma Gaussian error. This is the 1 sigma percentile error. You are going 34% on the 40, means 30% point of the data, they are lying on the left side within the region mean to 0.4 plus minus 0.47, and same way on the right hand side. So it should be very clear in your head how to explain these results. Okay, fine. This was for the 1D. Let me try to complicate it a bit further. What I'm doing now, I'm going to give you this exercise. I'll show you the program. I'll give you the program as well, but I would like you to work on it. Okay. How is it? Let me just do this x comma. Yeah. Can you see this distribution now? What is the difference between this distribution and the previous distribution? Anyone, please tell me. How is it different from the previous one? Yeah, it's x and y, it's 2D. Now, it's not a simple one-dimensional distribution, it's two-dimensional distribution I am having. The way I was telling that chi-square will work up to 2D, beyond that. So that's why we are starting from 1D, now 2D, and then further 3D, 4D, up to depending on how many parameters, unknown parameters you are having in your analysis. So let me run it. Okay, run anyway. Too many sessions it's giving me. Let me close a few programs, otherwise it will not run, I think. No terminate. Okay. Yes. I'm terminating all of the session. Just give me a while. I hope it shouldn't run now. Okay. So yeah, it's running. So what I have done, similar to the previous program, now I have defined the function, plotted it. When you will plot it, I'm plotting it using the plotly. I have told you yesterday as well, plotly is a very good library to plot in Python if you want to work with the interactive plots. In matplotlib, you can use the plot and plot them. They will be static plot mostly, but plotly will, matplotlib will give you very static images or plots. But if you work with plotly, that will very beautifully will give you these interactive plots. Okay, so with which you can play, you can rotate. It's a 3-dimensional plot. Now I want to show you that behavior of that particular distribution. You can see this is a 2-dimensional distribution function that I'm showing you. Now our aim is to sample it. Sample it by using the MCMC. Okay. Now you can see the behavior of this distribution. If you look from this, this is going to give you the behavior along X. So just have a look. This is along the X. If you are going to plot it like this, this is going to be the behavior. Along the Y, it seems like a beautiful Gaussian, but along the X, it's like a distribution which is having this again that local maxima over here. Okay. So now when you will be working with very realistic problem, they can be very difficult or very complicated dimensional space in which you have to work. Now my aim is to work on this. I'll not make any change in my program, the same program that I have written, but now only I'll add one additional parameter. Instead of A, along with that, I'll be having a B chain as well. B will be saving all the numbers corresponding to Y. Now you have to be very specific. When you were throwing the chokes yesterday in the for 1D problem, then you were throwing a single random number X only. Now here, because you will be throwing the random numbers in 2-dimensional space, so every time a single initial seed must be carrying 2 values, one corresponding to X, one corresponding to Y. Yes, every point. If you are working on a problem in 3D, every single seed will be having 3 independent value, one corresponding to X, another Y, third one corresponding to Z. Am I making sense on this? Fine. So that's what we are doing. We are starting with a point A naught value -5, B naught value -2, running this 50,000 time. Burnout time I am choosing 100. Proposal function I am again choosing it to be Gaussian with certain variance. I hope now this terminology must be making sense. Same program. Now just adding this B new, calculating same alpha. Now alpha is greater than u, then I am accepting, because that's the Metropolis algorithm. If I'll make it equal to 1, u equal to 1, then it will become simple. Acceptance, rejection, you can again play with it. Same program, nothing special about it. Appending all the values which are following the condition and plotting it. Now, because I am having two independent chain, this is the first chain corresponding to X. These are the random points which are accepted random points corresponding to X. These are the random points corresponding to Y. I think this image must be giving you a better idea of burnout phase. Why is it important for me to remove the initial points? Am I making sense? In this one, you see, if I'll not reduce initial 5,000 point, this is going to give me a very bad result, a statistical result, because my chain is started converging after roughly 6,000-7,000 points, and then that chain is completely converging. But before that, if I'll keep these points as well over here, this 5,000 to 8,000 points in my analysis, this is going to give me some trouble in my state. My result would not be very like convincing for me. Okay, do it. That's simple. I'm not running it because it will take some computational time. And if I'll plot it, I'm plotting it only some points along the X. Now you are plotting it along the X, something like this. Let me plot it. Okay, let me just show it to you. Let me show it to you. Same analysis I'm showing. Let me go to the, yeah. Now see. Now just try to focus on this plot. Have you seen this kind of plots? These are the corner plots we generally plot. Now, obviously, when we try to run our because it's a three-dimensional plot. If you are publishing a paper, you cannot plot on a paper, you cannot plot a three-dimensional plot over a screen. I rotated. The moment you'll go into the 4D, even in computer, you would not be able to simulate that or like visualize that. So obviously, that's why we figure out this way, that instead of giving plots like this, we are going to give these contour plots corresponding to different relations. Let's say I was having only two parameters, one X and Y. So these histogram kind of plot, the top one, this one over here. Yeah, I am having this powerful laser today. Okay. So this one is giving you the PDF or the distribution corresponding to X. This one is giving you the PDF distribution corresponding to Y. And this one is telling you about the correlations. Now remember one thing, here you will be seeing this density. These densities are the representation of the density of data points. More red is it in this one, I have made it to be red. More red is it in a darker shade of red, means the density of data points is very large over here, because this is a two-dimensional projection in the XY plane. Okay, so you will see the projection this one over here is it telling you about the that local maxima that you are having density over here, and then you are having these maxima over here as well. That's the global maxima. Okay, that's way these are the kind of histogram that you are getting in this particular analysis. This is the data which you can say that you are spanning the whole space. One thing that you can tell me from this, you will see this is X is like this, Y is like this. They are completely perpendicular to each other. You don't have any diagonal elements. You don't have any data points which is somewhere like this here. In this region, you don't have. In this region, you don't have. What does it tell you? That there is no correlation between the X and Y. Why is it so? If you'll go back and see the PDF that we were plotting, we were not having any cross term between X and Y. Now, homework that you can try to do, just have a look again on this contour. Now, the task all of you can go back and try to do is the following. The PDF that with which just wait for a while. Yeah. Have a look on this PDF that we have created. Over here, this is the X term and this is the Y term. Because we are not having any correlation between the X and Y, plus add 4xy in this distribution, because that 4xy will be a correlation term between X and Y. And then try to do the whole analysis again. And then I am hoping that you will be getting a correlation between X and Y. Then that plot will not be too perpendicular, like X is one along X and Y. So that's why so now you can see that contour is also not only telling you about the sampling, it's also telling you about the correlation between the parameters. So when you will be plotting it contour with the two parameters, it will tell you what is going to be the best fit region. It will also tell you what is going to be the kind of correlation between the data. Okay. Am I good till this, or are you get adjusted? Oh, yeah, please tell me, ask me. Yes. Hmm. So heat map, see, again, heat map is going to provide you the same information. But here you are having one freedom. I have given you this PDF. This PDF, who assumed this PDF? I myself have chosen this PDF. But if I'll give you the data, I'll give you the model, and you are creating a likelihood for yourself, then it would be very difficult for you to create the heat map. You can do that over there as well, but then those forms are not going to be that simple or traditional in that way. And even in the heat map, generally when you create the heat map between two parameters with some color scaling, over there you are supposed to calculate the value on all the parameters. Only then you will be calculating. But for that as well, you will be using some algorithm. What algorithm you will be using? So just don't think about heat maps like I'll write down a command in the Python like plot contour, plt.contour, and it will plot it. But what is going behind it, how reliable that heat map would be for you and useful for you, that you have to figure out. Okay. In 2D, again, let me repeat, if you are having 2D, plotting a heat map will provide you a lot of information. The moment you will going into higher dimensional space, you are having 4-5 parameters, what kind of heat map you will plot? Then you have to plot see the correlation between x, y, x, z, y, z, z, some w, is that way. Yeah. Yes, please. Second question. Yes. Yes. Hmm. Hmm. Okay. No, see, why higher? See, eventually, whenever you do statistical analysis, it's not a good idea to, like, you are creating so much data by investing so much computational investment you are making, and then you are not using that data at all. So if you are running, you have created such a large number of, see, more data you will create, statistics is going to be relevant with very large number of data points. So larger the number of data points, and independently, if you are creating, that will be giving you the behavior of the whole space. Okay. It's like if I'll say, let's say I'm talking about, I'll choose 5 of you. Okay. And then I'll say each one of you can work only, like you can move 20 steps per person. Okay. So one person, and then I'm saying, depending on your movement, I'll be seeing where these pathways are going. I want to see where are the pathways and which are the blocked region. Okay. Now one person is standing from the podium. By 20 steps, he'll be going by that part only. Obviously, that will not be the complete representation. I'll not be knowing about the rest of the space. But wouldn't it be a better idea? One person is standing here, another one is standing here, one is standing over there, and they will start independently taking their 20 steps. Then I'll be knowing, okay, there is a pathway, there is a pathway, there is a pathway. So in that way, I would be able to cover the whole space with the given number of steps. Okay, that's the strategy we are using over here. So to scan the complete space. Okay. Yes, please. Yes, obviously. Just that's what you should check this. Yes, we are giving. That's what the meaning of the walker. That's what I want to point out. That's what I was saying. Let me focus. Just okay. That was the previous program, I think. Let me. Just give me 1 second. That's what we were doing. If you notice this, See, oh, okay, just a while. What A note I am choosing? A note is a NP dot random dot uniform between -2 to 2. So what I'm choosing, I am choosing those 10 random points that will be a random number between -2 to. So now my walker will be anywhere in between -2 to 2, and I'll be choosing the position of the random walker independently. Okay, so I'm not choosing. Obviously, there is no point of starting from the same point. What would be the benefit? Okay, fine. Is it fine? Again, my suggestion would be the same program. If you are starting with one walker, it will not give you any benefit. Run with a large number of walkers. Are we good till this point? Now let's work with some real data. Okay, let's work with some real data. Before that, let me just give you an idea. Here now we have learned one part, MCMC, which I am talking. Given a distribution, you know how to sample. Now let's say very briefly talk about something called Bayesian statistics. Okay. So I have, even yesterday, I have shown you something called Bayesian. Bayesian. Okay, even before Bayesian, yesterday we have learned if you are having a data D, I am defining, and a model given by theta. Theta is some model parameter. Okay. So depending on that, what we were trying to write down, we were writing something called likelihood. You remember likelihood form? Yesterday we have written that form of likelihood in our slides. So if you write down likelihood, likelihood is given by probability of data given the theta. So this is a conditional probability. Are you familiar with the conditional probability? There is something called joint probability function. Then joint probability function is going to be something PAB is going to be PA by B PB, something like this. So means joint probability function of A and B is going to be this quantity times the probability of getting B independently. This is the joint probability. This is the conditional probability. And conditional probability is nothing but conditional probability is the probability of getting A given that B is true. Okay. I hope those of you must have done basic knowledge about having knowledge about probability. You must have come across the conditional probability. Okay. So similarly, likelihood is nothing but probability of getting the data given the model. This is the likelihood. Bayesian suggests that you can find out the probability of theta given the data. Probability of getting the model parameters given you have the data. Okay. This is going to be related to likelihood in a way P d by theta, d conditional theta, P of theta divided by PD. What are these terms? This term, we call it posterior. This term over here is likelihood. What is this P theta? P theta, we call it, let me highlight it, it's very important. We call it prior. Okay. This one PD, we call it evidence. This is evidence is nothing but it's like a normalization factor. If you are having a PDF, you are dividing it with some certain constant, it will work as a normalization constant for us. Yes, ma'am. Yes, ma'am. Prior is also a PDF. Yes, prior is also going to be PDF, but I'm saying PD in the denominator, ma'am. Yes, yeah, I'll have a discussion about P prior separately, ma'am. So yes, it's obviously going to be a PDF only, ma'am. So what is this prior? Means eventually what I'm saying, if I'm going to write down, I'm saying posterior is nothing but proportional to the product of likelihood multiplied by the prior. So obviously likelihood we have seen this was a probability distribution function. even the prior is also going to be some information about the distribution of theta. What are theta? Theta are the modal parameters which we are not known and which we are not aware or familiar with. Now, let me take some example. Those of you are familiar with the cosmology, briefly, not very detailed. I'll take the example of Hubble parameter. Are you anyone who is not at all familiar with Hubble parameter? Can you raise your hand? What Hubble parameter do mean? Rate of expansion of universe. Yeah, A dot by A quantity. Now, let's say you are having that Hubble parameter. When we write down a very simple model of Hubble parameter, it's a model called lambda CDM model. Okay, lambda CDM model of cosmology, where we assume that the universe is having components like the matter density, which includes baryonic matter plus the dark matter, plus rest of the energy is going into our dark energy. Okay, these two components, matter density and the dark energy. In that particular one, we know that there is a matter density. Now, I have collected some data. I have a model. In my model, I am having model parameter. One is the matter density, that you know that 30% is the matter density. Remaining 70% is dark energy. And there is one parameter called H naught, which is the Hubble constant, present value of Hubble constant. Okay. I'll give you independent data. You collected some data from somewhere. But along with that, you must be knowing some information about these parameters from some independent analysis. That analysis, the value, the information that you are having about your model parameters without looking on the data beforehand. You don't even have any, like, for example, you are doing this simple in your BSc first year, you started working on simple experiment on finding out the value of G by that pendulum, simple pendulum. But beforehand, you know, even before starting the experiment, you know the value of G through that experiment is given by 9.8 at that particular value. Now, knowing about your parameters even before doing the experiment is known as the prior information on the parameter. Okay. This is the first. Prior, I think it's making sense. Now, there is going to be second thing, which is going to be credibility or reliability of the prior. What is the credibility and reliability of the prior? It is the trust that you do have on your information. Okay. Now, whether the information that you are having about before doing the experiment, whether you trust that value or not, that's going to be a thing that you have to consider. Now, if I am very, very confident about my experiment, some scientist has done some experiment. If I am very much reliable or very much confident about my prior information, then what I'll say, okay, I'm saying the value of my this particular parameter might be coming from a Gaussian distribution, because Gaussian distribution gives you emphasize or more weightage to a single point. Let's say I'm talking about G. I'm saying I'm very strongly believing that the value of small g should be 9.8 only. If I'm trusting that, using that a prior information, giving it a distribution which is like a Gaussian distribution, then what I'm doing without doing my experiment, I am kind of biased. I'm saying, okay, even before doing experiment, I'm thinking, mera result 9.8 aana chahiye, something. Yeah, I'm biased towards it. But if I'm not biased, what I'll do, I'll say, okay, I'm a bit more concerned. I want to see how my data is going to give me the information. Instead of choosing 9.8, I might say, okay, let me give it a distribution. Value of G might go from 5 to 15, let's say. Okay. So 5 to 15, let's say yesterday we had this talk on Chandrayaan. Someone is doing this pendulum experiment on Chandrayaan. We don't know. We don't have a very credible experiments over or prior information. What should be the value of G over there? If you'll go over there, then you are not going to choose a prior Gaussian distribution which is having mean 9.8. Instead, you don't know what kind of G value you will be having. You know there is no anti-gravity, so it should be greater than 0. And you know the density is less, so it should be less than Earth. So what I'll do, I'll choose a prior. I'll say value of G can be anywhere between 0 to 10. Am I making sense? So my prior information, if I'm doing an experiment on moon, then my information, prior information would be for G. I'll choose the value between 0 to 10. I'll not I know the gravity is less weaker than Earth, so it cannot be greater than G, but it cannot be, and there is no anti-gravity, so it cannot be zero, below less than zero. So I'm choosing that prior. There, I'm not biased towards any value. My experiment will be giving me information. Okay. So whenever you read any paper, whenever you, because now I want to work with the posterior, you need to be very, very careful about the choice of prior. The choice of prior can completely change your analysis, completely change the answer which you will be getting. Whether you trust it more or less, it should be very. In case, whenever you read a paper and you are doing some MCMC analysis, if the paper hasn't quoted proper priors, then either you write to the authors and ask them. That's why you will see in the different papers, you will be finding out different result with the same data and the same model. Why is it so? Which result you will trust? Because people might have used different kind of prior information. There are different kind of trust level on the input values. Depending on that, that prior can change. Am I making sense?
Why? There is a part.
Yes, yes. So again, the amount of bias we are inputting. If I'm saying it's 9.8, my amount of bias is very strong. The moment I'm saying there is no anti-gravity, yeah, means that's completely on my, that's why it's a prior information. It depends on the trust level of user. If I'm working on a project which says there can be anti-gravity, then I'll make my prior like broader in that particular sense. In the matter, the example that I'll show, I am saying about the matter density of universe that should be 0 to 1. What I'm assuming in that case, omega m, I'm giving 0 to 1.
Sir, the screen is gone blank.
Give me the permission.
Yeah, yes, I can see it.
I'm really sorry for this.
Where are you? Yeah, yeah.
Placement.
Sorry, sorry. ठीक है. ठीक है.
Yes, ma'am. Yeah. Okay. Sorry. Okay. So what we were discussing, I was talking about the prior. So means the choice of prior is going to be very crucial in the Bayesian statistics. What kind of trust you are inputting in your system. And even in our analysis, we'll try to see if you are going to make different choice of prior, how your result is going to get impacted. Okay. Before that, what I'll be doing, I'll just give you the few steps of analysis. So if you'll see, if I'm considering likelihood you have seen earlier. Okay, likelihood you have seen earlier. Prior is again going to be a PDF. This is also going to be a probability distribution function. It can be anything. You can consider it to be coming from uniform distribution. It can be Gaussian distribution. You might be having some other choice. It's up to you. What kind of trust? Let's say you are having a parameter which is not going into the negative domain. You can choose it to be, let's say, certain distribution. You are knowing that it having prior information, it will go exponentially. So you can make any choice about prior, but be sure choice of prior is seriously going to impact your analysis. You have to make it very carefully. Okay. That's a very crucial point. Now, obviously, when I'll be writing down my program or computational power, you will see all these likelihood x at least is a function of e to the power minus x square, something of e to the power. If I'll keep putting these numbers, e to the power minus x square, these numbers are going to be either very, very large or very, very small. Yeah, very, very small in this particular case. If x is going to be very large, the numbers are going to be very small. Then our computer do have this issue of, or the limitation of at what precision we want to work. So wouldn't it be better if I'll take the logarithmic of both the sides? So what it will be, log of posterior will be proportional towards going to be log e base I'm taking, or ln whatsoever you want to write down, likelihood plus ln of prior. So log e or ln whatsoever you prefer to use. Okay. So log likelihood plus log prior. So instead, see, log function do have this property, means obviously taking the log of a function, it will change the shape, but it will not change the position of maxima and minima. You can try to do it. Choose a function, exponential function, take the logarithmic. The shape will obviously logarithmically will change, but the position of the maxima in the space, that will not change. And we are not interested in the all the numbers. We are interested on the where at what position of x and y our maximas are lying. Our interest is in that particular case. So we are going to work with the log. So what I'll do, I have already shown you in the previous discussion session how to find out the likelihood. I'll again show it to you. I'll make a choice about the prior. I'll take the log of that. I'll add these two, and that addition of these two will give me posterior, logarithmic of posterior. This is my Bayesian statistics. Now, once I know the posterior, what I'll do? I would like to sample it. How would I sample it? I'll write down the same code that which I was writing for my previous two programs. Same program I'll run with this posterior and will try to get my answer. Just for that, let me briefly show you the distribution that we were having. Have a look on this. Oh, yes. Now have a look on this likelihood. Log of likelihood will be minus of this particular chi-square. Agree? If I'm considering my data points to be Gaussian. Why I'm considering Gaussian? Because based on the center limit term. Okay. Now I hope links must be, you must be able to catch the points. So what I'll do, log likelihood is going to be nothing but my minus of chi-square. I'll define my minus chi-square, which you generally write down the program. I'll choose a prior. I'll add both of those, define the likelihood, run my own program, which I am having, because this is depending on the model. I'll try to do the analysis. Let's try to write down the program for it, and let me go through because I have already written it. So, sorry, I need to just, because I have terminated the program. So, okay. Okay, so is it visible to everyone, please? Okay.
Yes.
So now what I'm having in Hubble data, those of you are familiar with Hubble, you must have seen this. Those of you are not, consider it to be any data. Okay. I am having three data, Z, HZ, and sigma HZ. These are the three corresponding values, corresponding data I have plotted. Now, what I have done, if you'll plot it, it will give you something like this. This is having error. Okay. Data having error in itself. Okay. Fine. So it's the same. Now it's going to be, previously I was showing you very simple picture. Now it's going to be multi-dimensional, very complicated space which you want to scan. This is the model. Those of you are familiar, it's the simple lambda CDM HZ value coming from the Friedman equation. Those of you are not, consider it to be any functional form. Okay. What are the unknown parameters in it? H naught and omega m. Omega m is the matter density and H naught is the Hubble constant value. Okay. First thing I did, because I was having data and log of likelihood, because instead of defining likelihood, I'm interested in log of likelihood. I am defining simple chi-square and taking the minus. Just have a look. This is nothing but HZ minus H naught on that model divided by 2 sigma square. This is the chi-square. That's how you'll define the chi-square in your program. Okay. Just write down it. Either you can define it, the other form as a simpler, different function, and you can, I have just directly written H naught omega 1 plus Z cube 1 minus omega under root 0.5. That's the functional data. Still having two unknown parameter H naught and omega m. These are the parameter in which I am interested to figure out. Okay. And SSZ is the data error in the HZ, ma'am. So this I assume. Okay. It's a bit slow, lagging in. So Z is the data, HZ is the mean value or the values we are assuming. SHZ is the error in HZ. Remember one thing, again, I'm pointing out where what I'm assuming over here, I'm assuming each and every point is coming from the Gaussian distribution. Okay. So every HZ independently and each value is independent to each other as well. In case these are going to be correlated, if there is going to be correlation between the 2 points, the form of chi-square will change. I can briefly talk about it, but after this. Okay. Now, this is my likelihood. If I'll plot my likelihood only, this is something of this sort. Now it's two parameter. I have fixed one parameter. I have chosen H naught to be some 70 value. I'm plotting it. Other parameter, you can plot it like this. In 2D, plotting is easy, but more parameter, that would not be fine. The space, just the, okay, just the posterior, if you'll see, it is going to behave like this in 2D. X-axis is omega m, another axis is, y-axis is omega m, and this x-axis is Hubble parameter. This is the kind of space you are having. 3D, I can plot it for this one. Not possible in higher dimension. Now, the second thing, I need to add the prior. This was my log of likelihood. Now I have to take the log of prior. What can be the prior? I am going to talk about two choices. One, firstly, talk about the choice of the Gaussian prior. What is P? Have a look on this log prior. Can you tell me? I'm saying it's the Gaussian. Can you justify it why I'm saying it's a Gaussian? Log of Gaussian will be again x minus mu whole square by 2 sigma square. Exponential you will take. Yeah, that exponential will go away. So when I'm talking about the log of Gaussian prior, Hubble parameter, I'm saying, if you'll see, I'm saying I must be having some prior information that the Hubble value is 70 with error. How much error? 3. So I'm trusting on a random, someone independently have done an analysis, might have give some result, 70 plus minus 3. Some of you will not rely on this value. Some of you will say, why we are trusting some random value? Let's believe on the Planck result. Planck has given the value 68 plus some 0.3 or whatsoever. Depending on the trust on what result you are relying, you will choose that. Okay. Omega m, all of you must be knowing that we consider that 30% matter without doing experiment. I'm using it to be 0.3 plus minus 0.1. These are the trust I am putting, and then I am giving it Gaussian weightage. That's why I am calculating H naught prior plus omega prior, because these are independent prior. Logarithmic mein they will add. If I'll not do log, then they will multiply. Okay. Is it making sense? because that's important. Next, this is one choice. Another choice can be, I am not very much trusting any result. I want to independently do my analysis. Then instead of that, what I can do, I can choose a uniform prior. What does uniform prior mean? That I'm not giving any specific choice, but I'm saying Hubble value can be anything between 50 to 100, or omega m value can be anything between 0 to 1. It is very much similar. When I was giving you example of G value on moon, I can trust it can be anything between 0 to 10. Okay. So that's what. So these are two different kind of priors that you can choose. Okay. Depending. So first one, uniform one, I am giving the name uniform prior one. Gaussian one, I am giving name log prior 2. Okay. So let's see what we'll be using over here. What I will do next, I want to write down my posterior. Posterior, log of posterior is going to be log of likelihood plus log of prior. Over here, I am doing the same thing. Log of likelihood plus log of prior. I am choosing log prior one. So maybe in this analysis, I must be using the uniform prior. Is it clear till this point? That was all about the Bayesian statistics. Now, what I'll do, I am already having my Metropolis algorithm code. This is a PDF for me. What I'll do, I'll sample it. The same program, 2 parameters program, I have copy pasted the same program, previous PXY program, copy pasted it over here. And instead of function, wherever I was having the target function, I'll just change it with my log posterior. That's the only change I'm making in this program. Once I have done with this, I'll do, okay, this is the PDF. This is the 3D plots I have created. Let me go on to the, so here, okay. I have written a very short note, brief note. When I'll share it with you, you can read more details, whatever I'm saying. This is, I'm explaining proposal function and everything. So, see the change in the difference. Firstly, focus on the program. A note is the Hubble parameter. Initial value, I'm giving it 70. B note, 0.3. I'm a bit, because I want to reduce my time on the burnout phase. That's why I have chosen these values. There is no point of choosing initial. It could be anything. S, 5 lakh points. I'll be running my program 5 lakh times. Burnout time, initial 1000 point. I don't want to consider in my analysis. A new, B new. I'm choosing initial seed. How many steps I'm okay. This is one single step I'll doing. Focus on alpha. Alpha is nothing but, is it visible? Yeah, alpha is nothing but log posterior divided by log exponential. Okay, so because I'm taking the log, this minus sign is coming over here. Okay, fine. Okay, if I'll do this program, same analysis, comparing it with you, saving the same program, then I am calculating something called acceptance ratio. Acceptance ratio is nothing but how many chokes you are throwing and how much are getting accepted. So acceptance ratio is 0.84. When you run a program, it's very important that you calculate the acceptance ratio. If you are running a program where acceptance ratio is below 60%, or let's say roughly, at least give this criteria around 60 or 55. If the acceptance ratio is below that, that means your algorithm is not working very well, because large number of dots that you are throwing, you are rejecting them. Okay, then you either need to change your posterior shape of your proposal function, change your prior. But if you want to get a very efficient result from your algorithm, then try to manage your parameter in such a way that acceptance ratio on a higher side, above 60%. Over here, I am choosing the kind of choices I have made. My acceptance ratio is coming out to be 0.84. It's a good to go case. Nothing but I'm plotting the same parameter, n chain, the same plot. I hope these plots must be making sense. Yeah. Plot the same thing by using corner plot. I'll show you the corner plot. I'm getting this result. Okay, 1 second. Have you seen these kind of plots? So most of you must have seen. This is the a two-dimensional corner plot. On x-axis, this one is providing you the information with the analysis that omega matter is 0.33 plus minus error. Now you understand, just 0.33 is not mean it's the median value, with plus minus sigma 34% percentile on positive side, negative side. This is the result. This is the histogram you are getting only for omega m. This is the histogram for H naught, which is suggesting the value 68 plus 2.1 and minus 2.1. Now try to see this one. Over here, it's clearly telling you that there is a very strong correlation between H naught and omega m value. Can you see? This banana kind of contour. It's showing that if in case H naught is going to increase, then omega m value will decrease. So it's a negative correlation between. Had it been a simple circle, then I can say there is no correlation between two parameters. Had it been a banana shape structure in the this like on this diagonal, then I would say there is a positive correlation. Okay. This darker region is nothing but this is the density of the points, larger density. The more you are going outside, you will see this density of points is decreasing. Means most of the points are clustered in around the your maxima in between, and further you are going, that's a sample is going to have less and less numbers. Okay, fine. Am I good this point till this point? Any question related to it? Because this was the example program. What I'll suggest, because I cannot teach all the syntax, that would not. I'll just say, because there is nothing about. When I was even yesterday I was talking about, if you want to learn any programming language, there is learn how to define the function, how to define arrays in the program, for loop, if loop, syntax, how to read a file. These four things you learn, you will good to go with any programming language. There is nothing more in Python or Java or any programming language. If you know how to work on these four things, focusing on these four aspects, and you are good to go. Okay. So code, I hope all of you will understand very easily. It would not be issue, but the point was to understand the physics. Yes, please. No, see, there is no relation between burnout and the choice of prior. Burnout is nothing but, in this program, I have chosen my H naught value to be 70. Generally, we know that the Hubble parameter is roughly around 70, 68 or 73, something of that sort. Okay. Now, let's say I want to play with it. I choose my initial seed to be 200. Okay. Now, obviously, my program will not immediately jump on 70. My chain will converge around 70. I am expecting that, but it will take for my program, it will take some time to start from 200. It will come on 150, 100, then come to 70, and over there it will start converging, oscillating around that value. But now the data that I have consumed over, or the steps that I have taken to come from 200 to 70, where my program will start converging, that of not much use for me, because that's the time I'm spending just to reach to the global maxima. So what we'll do, we'll get rid of that initial data. That's the importance of burnout phase. In my data, you will not see, because I started from 70, 0.3, and my results are also very much similar. But if how is it possible, and why do you think before and I must be knowing what would be my result? If I'm give you a random data, you will not be knowing what is going to be the result, should be the prior or a good choice of your initial points. Same additional exercise, what you can do with this, run the same program. I cannot run, it will take time. It will took me around 5 to 10 minutes to run the whole program, which we're not having that liberty here. So run this program for Gaussian prior as well. Try to see the difference in the result. This program I am running for single chain. Modify this program, run it for the multiple number of chains where you will be having multiple seats, because previous program you are having. Try to see how we have done it over there. Try to do it, replicate it over here as well. Okay. That's all from this one. Now I just want to last thing. Do we have time, ma'am? 5-10 minutes. Okay. So I'll just take 5 more minutes to go through a package called MCMC. Okay. Same data, nothing special, but I'll not be talking about the internal working on it. I'll just name it. Similar to Metropolis algorithm, this is based on a algorithm which is known as Z sampling. And Z sampling method is in better. In Z sampling approach, you need not to worry about the choice of proposal function. I was talking the Metropolis function, you have to choose that size of the proposal function, what should be the variance. In Z sampling, you need not to worry about it. How, why? That's a detailed paper, research paper by the authors who developed this Z sampling or EMCMC. I can give you the reference paper, one can read about it. But for timing, I'll just let you know about the working. Okay, just a minute. So same data I'm working, same example, Hubble data, Z, HZ, SZ, no change, same plot, same likelihood. Okay, I'll go my program. Same likelihood function, the way we did in the previous session, taking the log. I'm just plotting it. It's the simple plotting of my histogram with respect to one parameters. Then 2D plotting, you can use Plotly. I am using for plotting it that I have told you. So this is the kind of histogram 2D you can do. Then add prior, same prior, either add prior 1 or prior 2 depending on your choice. In this one, let me see. Even here I am using the prior 1 only. You can run your program, same program using prior 2. You will see the result. Till this, everything is same that we have discussed. In the previous program, what I was doing, I was copy pasting that code from Metropolis testing. Now over here, instead of doing that, I'll be writing this program in which I'll be using the my program of MCMC. Okay. Now, when you run this program using MCMC, you are going to be a bit smart. How smart? I'm saying chi-square is not providing you good result. I'm saying chi-square, that's why you are going on MCMC, because chi-square is not efficient. But it's not providing you right result, but it's not providing you more accurate result, but it's going to provide you some tentative results. So what MCMC, when we try to run this eMCMC package, what we do beforehand, before running on our real code, to know the tentative value of my initial seed, because initial seed is, as a user, I am supposed to provide. Instead of providing it by hand randomly, what I will do, firstly, I'll try to run a simple chi-square analysis on my program and try to find out some tentative results. And those tentative results I'll use as an initial seed. That will give me the freedom that my burnout phase, I need not to go on a very large burnout phase. Okay. So that's a smart thing one can do. So to get the tentative result. So that's what we have done. We have defined chi-square is, all of you know, chi-square is -2 log of our likelihood. So here I am applying the same on posterior. This is the program inbuilt library. There is SciPy. Are you familiar with SciPy library in Python? SciPy is for the scientific Python. NumPy is the numerical Python. Okay. SciPy is having a lot of library on the linear algebra of data fitting and everything. I'm using that one of the inbuilt library to find out the parameter. So this piece of code is nothing but I'm applying chi-square, find out some tentative result. Those tentative results I am going to use the initial seed. So this program is nothing but just figuring out what could be a better choice of initial seeds, because that's the input. I don't want to rely on the unknown program. Okay. So that's what, how many, okay, let me just go on this. These commands, I'm installing the eMCMC package. I'll run it. I'll not run it. It will take some time. Even installing eMCMC on the Google Colab, it might take 4 or 5 minutes. So I'll just showing you the program, is explaining the steps. Fine. Just go through these parameters. Number of dimension. I'm working on a problem having 2-dimensional X and Y, H naught and omega m. Number of walkers. Number of walkers, we are choosing 2. Oh, sorry, 6. I'm saying I'll choose 6 values, input initial value. So what I am doing, I'll calculate a value from chi-square. Okay. And in that chi-square initial value, I'll add certain error. So that error, 6 different errors. So one around that mean value, chi-square value, one walker will start from here, one will start from here, one will start from here. I have created such 6 combination of initial points by using chi-square analysis. Each walker will be moving 10,000 points. Each walker, one will start from here, go that way, one will go that way, will be walking 10,000 steps. Okay. So if you'll see, this command is nothing but these are the initial walkers. So 68 and 0.31, this is the first walker position. Next one is 68.14, 0.31. If I'll keep showing you, these will be 6 initial code values like this. Okay. So these are the 6 initial position of the walkers that I have decided. But I am keeping them somewhere close to my chi-square value so that my burnout phase time will get reduced. Fine. That package that I have defined, the way you will import the programs, it is not taking anything else. emc.ensemble sampler, this is the way they have defined their program. What are the inputs? Number of walkers, how many walkers, number of dimension, 2 dimension, log posterior, which posterior you want to target function. Okay, a equal to 2 is the again the dimension you are talking. This input you will give you to your program, and then it will automatically inbuild program, whole program is written. It will give you the 2 chains, one chain of the first parameter, another chain of the second parameter. So whole EMCMC is here. This is the 2 lines. This is the code. So it's nothing but you are just calling the program and finding out these values. And all are the input values. So you are defining. So most challenging thing in implementing EMCMC for all of you would not be to use it. It's very easy, one line. The most challenging way task is going to be defining the posterior. That's the most challenging thing. Reason being, why I'm saying it is challenging. If you are working with a simple data set, it's easy. You will define the likelihood. But let's say you will see in the research, what will be, you will be having a data set of Hubble. You will be having data set of supernova, one data coming from galaxy clusters, one data coming from some other parameter. Each of these models, they are going to have their independent parameters as well. Hubble is having H0 omega m. Supernova will be having some other parameter, some alpha beta parameters of their brightness or slope. Galaxy parameter will be coming. Galaxy cluster you are using, there will be some parameter related to electron density or something. A large chunk of parameters. Now, how to add them and merge them, that's going to be the main challenge. Running the EMCMC is the second part. MCMC is very easy. If I'll run this program, same 6 chain, same program, the way I have did it. 6 chain for the H0 values, overlapped, 6 chain for the H0 values. Now I am going to plot the same contour. I am getting this one. This one I am getting from the EMCMC. So that was one program you are writing from the scratch, another one you are using the library. So I'll personally will suggest later when you will writing down, like working for a research project, obviously you have to use this because this is more efficient, will save you a lot of time as well. But beforehand, first, and if you are dealing with any data, write down your own program. Write down and work with Metropolis Hastings, because that will tell you about all the nitty-gritties related to the parameters. Only then, when you will be giving some inputs for your EMCMC, you would be knowing about what kind of value, what kind of prior, what kind of proposal, whatsoever choice you are supposed to make. So then you would not be using the whole device as a black box. Okay. Otherwise, it will seem like, okay, EMCMC, it's a package. I am giving it some input. You're getting some output. I don't know what is happening inside. So firstly, write down your own program, define your likelihood, run it with the with Metropolis Hastings. If it is giving reliable result, trust that. If it is not giving reliable, when you will be quoting the result for research or for your paper, only then shift to EMCMC. Okay. So I hope 2 parameters I have done. Now, what is your task? You take a 3 model parameters. Now you see 1 to 2 I have shown you. 2 to 3 is your task. If you are having a model which is having 3 parameters, then try to do it. In case you will stuck somewhere, by tomorrow, try to do it. You choose a model which is going to have some other additional parameter, same data. Those of you are familiar, you can work with something called XCDA models. Cosmology people must be knowing what is some dark energy model you can choose, some CPL model or some parameterization you choose. Okay. Otherwise, those of you are not familiar, add some additional parameter. The form I have shown you, no, the function that I have shown to all of you. This one, this function. Yeah. Add one more parameter, some additional C parameter, D parameter randomly. It's up to you. Okay. That might not be having any sense in that case, but at least that should mathematically should give you some answer. Okay. So add some parameter and try to see. Then you have to make certain changes in the program. Instead of 2 chains, you have to run 3 chains. That will give you how can you go from 2 to 3. And once you know 2 to 3, then 4, 5, it's not like would be a big deal for you. Okay. So that is EMCMC. Now let's see one thing. We started with this. I think we are able to do all the things which we discussed today. Yes, please. Now. Yes. 10 to the, in the EMCMC. Let me. Oh, so see what we are doing. See, result X. If you'll see, result X is nothing but these are the random. These are the value coming from the chi-square. Okay. Then what you are doing, you are adding some error in it because you don't want all 6 workers to stand on one point and you don't want to move them separately. What you are doing, this is, let's say this cup is the mean value coming from the chi-square. Then you are adding some random Gaussian error, 10 to the power minus 4 times some random dimensional error. It is making it to move one worker here, another random worker will here. So this is the amount of error you are adding in your chi-square result, so that all your workers are going to have different values. So you can change it if you want your workers to move very, very far. One worker there, you make it 10 to the power minus 2. So I have chosen it to be 10 to the minus 4 because I want my initial points to be different from each other. How different? This 10 to the power minus 4 I have chosen. Okay. Yes. Two. Okay. Variable coefficient. See, this is the problem with Python. See, I'll not say the problem, but this is how if you are writing a program in Mathematica gives you the freedom to deal with the variables. You can write down the whole program in the terms of variable, and then you can run it in like this. But Python is not going to be every function is going to be numerical. So every function that you will define, let's say I'm saying, when those of you are familiar with the cosmology, I'll just tell you, when you will be doing the cosmology with the supernova, then you will come across integration factor, because over there you define something called luminosity distance. Luminosity distance is going to be integration dz by hz. So over there some integration will come. Now in your likelihood, you are not just defining the function, even to define a likelihood, a integration will go. Now you have to write down your program in such a way that firstly that integration will get solved, then that likelihood will get defined, and then the results should be in the terms of numerical values, no variable. Your likelihood cannot go as a variable parameter. Yes, range of the coefficient you are deciding on the base to prior. What prior is doing. Prior, if you'll see, have a look on the prior that we were choosing earlier. This one, let me show you the prior only. What is this prior doing? This one. You have two parameters, H0 and omega m. You are just telling your analysis that it should go from 50 to 100. It should go from 0 to 1. Isn't it? You are restricting all the points beyond that. You are not, and why? See, remember, I am calling it uniform prior. Why I am calling it uniform prior? Because I am giving equal weightage to all the points between 50 to 100. I am giving equal weightage to all the points between 0 to 1. So that's how you can choose the range. Second is going to be Gaussian prior. In Gaussian prior, I'm not making a choice, but I'm making one point very prominent. I'm saying 70 plus minus 3 is very prominent, but here H naught value can go from minus infinity to plus infinity because Gaussian is minus infinity to plus infinity line. There is a possibility, a finite possibility that one value might come out to be very, very large, minus 200 as well. Okay. Over here, I'm giving that freedom, but the probability of that one is very, very minimal. One random point might come, but if I'm dealing with 10 to the power 6 point, one point will come, it will not change my statistics. Okay. Yeah. So here you are giving the complete minus infinity to plus infinity space. In the Gaussian prior, here in the uniform prior, you are restricting your parameters to come into this range only. Okay. Anyone else having any questions? Yes, please. Data. So if you are dependency, which data you are concerned about? H data though is publicly available. You will just search Hubble paper. Every paper will quote either the reference. Go on to the archive, write down Hubble. You will get papers. Either you will get the data itself, or you will get the like the link to paper. Either in case in my paper, in 2 papers, I do have the data whole compilation. You can, in case interested, you can search recent data or cosmic chronometers. Yeah.
Sorry.
It's okay, ma'am. I know.
Maybe
Time.
24
Yes,
okay,
yes,
sorry.
ma'am. I know.
I know
Okay.
everybody's enjoying the session, so am I, but I'm sorry. we have to
Yes,
cut.
ma'am. We have to. Yeah,
Yeah,
it's okay,
sorry.
ma'am.
Sure. So we are winding up, and 2:30 we'll be back here for the next session. That will be social.
Okay.
Yeah.
Those of you